This week, we start two dimensions. We will start our analysis the way that we have started the analysis for all of the other problems. We're going to start with a problem statement. In this case, what we want to do is we want to release a contaminant into a channel full of water and see how it disperses with time. Now, more likely what happens is some contaminant is released and you want to understand the environmental impact of that contaminant. We will use this problem for both our analysis with triangles and our analysis with quadrilaterals. Let's look at the mathematical problem statement. So again, the goal is to simulate the dispersion profile. We want to be able to vary Reynolds numbers. For those of you who are not familiar with fluid dynamics, think of this as the speed of the water in the channel. We want to be able to look at a range of salt concentrations, and we want to be able to tweak the boundary conditions somewhat. So when you're running the code and running a lot of various iterations, or rather parameter sweeps, we'll change parameters and keep running it. So this is one of those cases where having a stable code that you can rerun but just tweak so that you can analyze and look at different scenarios. This is where the code is helpful. Let's just take a quick look at the mathematical statement, starting with the assumptions. So we're assuming that we have plain Poiseuille flow. So that will mean that the velocity in x will be a function of y, and the velocity in y will be 0. We're going to release a contaminant. So that means we'll need a source term, because that will be the source of the contaminant. We're solving for the dispersion, so think of this is the diffusion term. In heat transfer it was conduction, but now in a more general sense it's the diffusion term. And finally, we'll still assume that we have constant material properties. So what does the governing partial differential equation look like? Well, we're simulating the concentration. So what we have is we have the change of concentration with respect to time plus the velocity times the derivative of the concentration. So this is our convective term, will be balanced by the diffusion term plus the source. So let's now think about building out our finite element formulation. And what I want you to notice as we do this is that you have seen virtually all of these pieces. There are some pieces that are slightly different because it's in two dimensions, but there's nothing that's really new here when we build out the continuous and the discrete finite element formulation. So our first step, we approximate C with C hat. And that means that we will have a residual that's a function of C hat. As we drive the residual to 0, this equation will balance. So the way that we're going to drive the residual to 0, remember we're going to do it over the whole space in sort of on average over the whole space, and that means that we have the weighted residual. And in this case, you can see that we have the 4 terms from our governing PDE, and we have our weighted residual formulation. The next steps are integration by parts, deciding how we're going to approximate C hat, and then forming the discrete approximation.